nanohub.org.
Online simulation and more for nanotechnology.
So good afternoon. Thank you for coming, and I appreciate the opportunity to talk about some of the things I've been involved with probably for about 30 years. So my interest in these scanning probe microscopes goes back to roughly 1984 when I first heard about their development. And for the past probably 28 years at Purdue, my research group has built and used these types of instruments to investigate properties of nanoscale materials. And rather than tell you about my research, I thought I'd try to explain to you how these scanning probe microscopes work. Because if you understand what they can do, then possibly in the process of your research or your work here at Purdue, you might find a need for it, right? So I'm not going to really talk about cutting edge results. I'm going to more focus on what the instrument does and how it does it to try to give you a sense of that, right? And if I succeed with that by the end of the lecture, then I'll be a happy guy. So to begin with, I'd like to just provide an overview of microscopy in general and try to emphasize a few points. So if you look at microscopy, right, it basically spans about 10 or 12 orders of magnitude in distance, right? Humans have been using their eye to see to see objects that approach a millimeter or so in dimensions or less, and they've been doing this for tens of thousands of years. To see things below about 1/10 of a millimeter, you have to start to use a light microscope, and the light microscopes were first invented in Holland around 1600, right? So a little bit more than 500 years ago. They were very simple devices at the beginning, but they have evolved considerably, and so nowadays just about every lab at Purdue has an optical microscope somewhere that you can use to see things below about a millimeter up to maybe the best optical microscopes typically end around a micron, right? 10 to the minus 6 meters. If you want to see below a micron, you need another way of seeing. And historically, these electron microscopes, they were invented in the early 1930s. And what they did is they used electron beams. They took a focused beam of electrons and they reflected it off of a sample, or they transmitted it through a very thin sample. And by measuring the amount of electrons reflected or transmitted through the sample, it was learned that you could start to considerably extend the range of the light microscope well below a micron, right? You could go all the way down into the nanometer length scale range, right? So these electron microscopes have been available for about 80 years, and they're also widely used in all labs throughout the world. The scanning probe microscope, which is the topic that I'm going to talk about today, that microscope was invented in 1981, 1982. It was invented by two scientists at IBM Zurich labs in Switzerland. And what it allowed you to do was it allowed you to see this nanometer length scale range with a precision that was unprecedented at the time the microscope was invented, right? So all of a sudden, the electron microscopes, which start to lose resolution at the nanometer length scale, right? All of a sudden they were complemented with these scanning probe microscopes that were ideally suited to see things below a nanometer. Now, of course, nothing is static in science and engineering. Everything is continually improving. And so nowadays you can find electron microscopes that actually can see individual atoms. But the scanning probe microscope distinguished itself very early on because it was able to see individual atoms on surfaces of materials back in the 1980 timeframe. The relative cost of these instruments, it's kind of useful to try to do a plot to show the expense. Optical microscopes typically are available for $5,000 to $10,000, a good one. And there are probably 1,000 of those microscopes at Purdue. I'd be my guess, just to do a rough estimate. There's probably thousands of optical microscopes. They're in every lab. Electron microscopes are divided into two categories. One is called a scanning electron microscope, and the other is called a transmission electron microscope. It's an SEM and a TEM, right? There are probably dozens of scanning electron microscopes at Purdue, and there's maybe a half a dozen or so transmission electron microscopes. The electron microscope distinguishes itself because of its cost. Right? The top end transmission electron microscope can cost upwards to $2 million, right? And there's only a few of those that are available, and usually they're available in a centralized lab where you have to take a class, and you have to go through a technician who actually uses the instrument for you. The scanning probe microscope is not as inexpensive as the optical microscope. The scanning probe microscope costs about $100,000 to $150,000. There's probably 20 to 25 of them at Purdue. There's about a half dozen of those instruments in this building, this Burke Center right here, right? So there's 2 or 3 labs that are devoted to scanning probe microscopy. And the advantage of the scanning probe microscope is that it's reasonably accessible. If you spend a few weeks of your time to learn how to use it, usually you can get access to it, okay? So it sort of bridges the gap between the optical microscope, which is everywhere, and these transmission electron microscopes and scanning electron microscopes, which tend to be localized in user-oriented labs, okay? So the remainder of the talk is going to be how these scanning probe microscopes work, right? I'd like to try and explain that to you because it's really remarkable how simple they are and what they can achieve. So what's so special about these scanning probe microscopes? Well, first of all, I have to remind you something about the optical and electron microscopes and what some of the characteristic features of those more traditional microscopes are, right? These optical and electron microscopes are very good at providing lateral information about a surface. So if you take a surface or a material and you want to see the separation or the distance between two objects on that material or on that sample, right? The electron and the optical microscope, as you can use them today, are very good at that. They provide lateral information, right? Unfortunately, the images appear very flat, right? You can do false color imaging of an optical microscope image to make it artistically appealing. But ultimately, the amount of information about the third dimension of your sample is not present, right? Only the lateral spacing or the lateral distances are accessible in the optical and the electron microscope. So it's very difficult to obtain information in the third dimension. The scanning probe microscope, on the other hand, extends microscopy into that third dimension. Right? So now you can not only get X and Y information, you can get information about how far things are spaced apart, but you can also start to get quantitative information about how high one object is with respect to another. And this was radically new, radically different in the early 1980s when these scanning probe microscopes were invented. In addition, people who use scanning probe microscopes have learned how to use them to manipulate, to actually move things around at the nanometer length scale. So this is not going to be a technique that's useful for manufacturing capability because it's very slow. But on the other hand, you can learn an awful lot if you have a small nanoparticle and you want to move that nanoparticle from point A to point B. Right? How do you do that experimentally? How do you move things at the nanoscale, one with respect to another? You can't just pick up a pair of tweezers and move them with tweezers, right? The scanning probe microscope allows you for this nanomanipulation capability. So this is really a unique feature of the microscope. And then one of the new trends that's been developed in the last 10 or so years is that you can actually use these scanning probe microscopes to obtain information about the mechanical and electrical properties of nanoscale samples. So if you have a material, an object which has nanometer size dimensions, you can actually start to probe its elastic properties, its mechanical properties, its electrical properties, right, with these scanning probe microscopes. And none of these three capabilities are really accessible to the optical and the electron microscopes that are more traditional. Right, so the scanning probe microscope very nicely fills out a region of space in science and engineering that was left open by these more traditional microscopes. Okay? So that's what makes the scanning probe microscope so special. I put this slide in to try to address questions that some of you might have, because if you followed any, if you've read any literature about scanning probe microscopes, you'll immediately know that there are basically two types of scanning probe microscopes. One is called a scanning tunneling microscope. The other is referred to as an atomic force microscope. The lecture I'm going to give today is going to focus more on this atomic force microscope, right? And I'll tell you how it works. It's completely different than the scanning tunneling microscope, which was the first scanning probe microscope invented. So scanning probe microscopy is a big area. It's a big umbrella. And there are a lot of individual microscopes under that big umbrella, right? And originally the first instrument was the scanning tunneling microscope. But nowadays, virtually every lab in the world has access to the atomic force microscope. It's a branch of scanning probe microscopy. So if you've done any scanning probe work in the past, I'm going to focus more on the AFM rather than the STM in this talk. Okay? So I just wanted to explain that up front. When was the atomic force microscope invented? It turns out in 1986. This is the paper that appeared in March of that year. I have to say a word about the authors. Binnig was a scientist from IBM Zurich. He came and visited Cal Quaid at Stanford, spent a sabbatical there. And one of the technicians who worked with Binnig in IBM Zurich, he's not a technician, he's a scientist. He also joined Binnig, and together at Stanford, they came up with this idea about an atomic force microscope. And this is the picture that they had in their first paper, right? What they imagined was a sharp tip with an atom at the end of the tip, and that atom at the end of the tip would interact with all the atoms in the substrate. Right? And the interaction of this atom with all the atoms in the substrate is a topic of considerable interest even today. And what they realized was that if they could control this force between the front atom on the tip and all the other atoms in the substrate, then they could produce a microscope which could map with atomic resolution the features that might be contained in the substrate. Okay? Very simple idea. Now, what makes this paper so special is the number of citations it has received in the scientific literature. Most of us, if we publish a paper in a scientific journal, we're happy if 20, 25 people in the world read it and cite it in another paper that's written in the literature. So if you get 20 to 25 citations per paper that you write, that's been a very successful paper. This paper is so important that by 2008, it had 5,200 citations, right? So it's hundreds of times more cited than most of the articles that professors at universities write. That was in 2008. I don't know what the number is today. But in 2008, the claim was made that this was the most cited scientific paper in the history of science, right? So the idea behind this was so far-reaching. It went and addressed so many fundamental problems in so many disciplines that huge numbers of people started to read it and tried to implement the technique that they devised. Okay? So it's a big paper. Good for those guys. They really had a great idea. It's important to understand how this microscope works because it doesn't work like an optical microscope and it does not work like an electron microscope. Right? This microscope measures forces. And so what you have to imagine is you have to imagine a sharp tip that's placed in close proximity to a substrate. And what do I mean by close proximity? I mean something like a nanometer. So the separation between the apex of the tip and the substrate is on the order of a nanometer, 10 to the minus 9 meters. When you get atoms that close together, there are atomic forces that come into play, right? And the lead atom on the tip starts to feel atomic forces associated with all the atoms in the substrate. In addition, there's a secondary force, which is the force that all these atoms feel by all these atoms down here. So when you're far away, right, this collective force between the tip and the substrate tends to dominate. And that force is often referred to in the literature as a van der Waals force. As your tip gets closer to the substrate, then the force between the lead atom on the tip and the closest 2 or 3 atoms on the substrate start to dominate the interaction between the tip and the substrate. Okay? So it's always a delicate combination of these two forces that determines the net force that the tip feels. Now, what is the tip going to do in response to these forces? Well, if the forces are attractive, let's say, the tip is going to be attracted toward the substrate. And if you suspend the tip, let's say on a spring, this is a hypothetical model, right? If you suspend the tip on the spring, and there's a downward force on the tip, the spring will stretch until a restoring force is developed in the spring that just counteracts the attractive force between the tip and the substrate. So the spring will stretch through a distance delta z. The spring has some spring constant K in newtons per meter. And if you multiply the spring constant by the amount that the spring stretches, the spring will exert a restoring force upward that will precisely counterbalance these atomic forces that are pulling the tip downward. And by measuring that displacement, delta Z, and by knowing that spring constant K, you could measure with very high accuracy the interatomic forces that develop between the tip and the substrate, right? So, in principle, if you took introductory physics, you would understand these principles. You may not know how to calculate these interatomic forces, but you would know that a stretching of the spring is counteracted, right, by this elastic restoring force K delta Z, right? And if you understand that, you understand how an AFM works fundamentally. The details are a little bit more complicated, but this is the basic idea. Okay? Now, what kind of value for K should be chosen for this spring? Clearly, if you pick a value of K that's very large, right, then you'll get a big force for a very small delta Z, and you won't be able to measure delta Z accurately, right? If, on the other hand, you pick a value of K that's very, very small, then delta Z is going to have to be very large, and what will happen is the tip will be pulled into the substrate, right? So you got to find a magic value for K. And it turns out from very simple arguments, if you just think about how these atoms vibrate in a solid, right? They vibrate at a frequency of about 10 to the 15 hertz. The mass of an atom in a solid is about 10 to the minus 30 kilograms. So from those two numbers, you can figure out what the effective spring constant is between atoms in any solid. And that effective spring constant is on the order of a Newton per meter, right? It's on the order of a Newton per meter. So that means if you want to measure these interatomic forces, you better make the spring constant K on the order of a Newton per meter, right? So the trick is to devise a spring that you could measure its deflection very accurately, and it still has a spring constant K that's about 1 Newton per meter, give or take a factor of 10, either way, right? So that's the challenge. That's the challenge in making these microscopes work. So, I'd like to briefly say something about these interatomic forces and try to convey to you some of the information that we now know about these forces, right? This has been a long story that goes back probably 70, 80 years, right? And I like to illustrate the discussion by just asking you to consider one atom that's made to approach a substrate in a very, very systematic way, right? So you just imagine this one atom being slowly pushed up to the substrate. And I want you to think about the forces that atom's going to feel, okay? Well, the interaction force is a function of the atom-substrate separation I've plotted down here, right? And all atoms approaching all substrates have a curve that generically looks like that. Initially, it goes negative, and negative means that initially the atom is attracted toward the substrate by these interatomic forces. Once the atom reaches the surface of the substrate, then there's a strong repulsive force that pushes it back again. So you can't push this atom through these atoms, right? Nature won't let you do that. What nature does is it provides a very strong repulsive force to push it back. So when the separation between the atom and the substrate gets very small, the interaction force rises very steeply and becomes positive, which indicates it's repulsive. So positive forces are repulsive, negative forces are attractive. As you approach the atom, this one atom to the substrate, what happens is there is a weak attractive force that develops when this atom is far from the substrate. By far, I mean a nanometer or so, right? That's not very far, but But when its separation is on the order of a nanometer or so, the forces are dominated by these van der Waals forces, which are electrostatic forces that are set up between this atom and all the atoms in the substrate. As you move closer, as you move this atom closer, right, chemical forces could take over, because now the electron wave functions, the electrons that are associated with this atom, can start to interact with the electrons that are associated with the substrate. And whenever you got electrons interacting with electrons, that's a chemical force, right? So you can actually start to feel, this atom would actually start to feel chemical forces. And if you continue to push it in, right, that usually sets in around 0.5 nanometer, 5 angstroms, give or take, right? If you continue to push it in further, right, this strong repulsive force sets up. And so if the force is attractive, negative here, if it's repulsive, positive here, there's going to be a region, there's going to be one point where the force has to go to 0, right? Go from a negative number to a positive number, you have to have a 0 force, right? And that 0 force then determines the equilibrium separation of this atom above the substrate. And typically that equilibrium separation is on the order of 0.2 to 0.3 nanometers, 2 to 3 angstroms. So if I just drop that atom onto the substrate and I measured how far it was from these atoms, I would get a number that would be 2 to 3 angstroms, which is of course just the separation between atoms in any metal or in any semiconductor. Atoms and metals and semiconductors tend to be 2 to 3 angstroms apart, one from another. Of course, the reason they're that distance is because there's no net force acting on them. That's their equilibrium position, right? So what this atomic force microscope does is it replaces this one atom by a tip, right? But it turns out when you work out all the arithmetic, do all the physics, right? The interaction force versus atom versus tip substrate separation strongly resembles this type of curve, right? So going from one atom to a tip of atoms doesn't really change the shape of the interaction force versus separation, right? And so this is the actual force curve, right, that dominates, that controls whether the tip is pulled toward the substrate or whether it's repulsed away from the substrate. As you shrink the separation between the tip and the substrate, right? It all goes back to this fundamental force curve, right? Now, how would you measure this force curve experimentally? I mean, why would you believe any of this I'm saying? Right? You believe it because you could make a measurement. And so how would you measure that curve experimentally? Well, it's really hard, right? You can shoot particles, you can shoot atoms at substrates and try to measure the trajectory of the atom, right? And then work backwards knowing the force versus distance to try to interpret the trajectory that's measured versus the force that's governing the motion. But that's a hard problem, right? Up until 1980, it was extremely difficult to measure the shape of this curve. But with this atomic force microscope, for the first time, we can systematically investigate this, and we can look and see if all these different regimes are there. And we can start to get an appreciation for how big these forces are, how strongly attractive, how strongly repulsive they might be, right? And this has all been enabled by the AFM, the atomic force microscope. So I'm not going to talk about the details of that, but it's extremely interesting basic science, right? It just knowing the shape of that interaction force allows you to understand all kinds of things. So I wanted to spend a little bit of time on that, right? I also wanted to spend some time on why is this a scanning microscope, right? Why is it a scanning microscope? And I try to illustrate that in a very simple way by asking you to think about a substrate which has a feature on it, right? And let's say this feature's got nanometer dimensions. right? What this scanning probe microscope is going to do is it's going to take a sharp tip and it's going to move that tip over the substrate in a systematic way. I've indicated a systematic way by these dashed red lines. So you basically raster the tip across the substrate, you move the tip up, you raster it back, move the tip, raster it back. You keep going back and forth, right? And all the while you're moving back and forth, you're trying to hold the force between the tip and the substrate fixed. So the force between the tip and the substrate is going to be your force, your distance sensor. It's going to tell you how far the tip is above the substrate. What happens when you encounter a feature? Well, the tip is going to have to jump up in order to keep the force between the tip and the feature fixed. And if you could monitor how much the tip jumps up when it scans over that feature, then you're actually measuring the height of that feature, right? So that's how you get the information about the third dimension with a scanning probe microscope. Now, some of you are probably saying, well, how good can that be? Because clearly the tip has to be very sharp, right? If you have a very blunt tip and you're scanning a very small object, right, you're going to have a distorted image, and the image is going to be distorted by the radius of the tip. So what you have to do is you have to learn how to make sharper tips, right? And the sharper you make the tip, right, the better resolution you will achieve when you try to image these nanoscale features on substrates. So the trick is to make sharp tips and to control the motion of those tips back and forth as the tip moves across a substrate. Whenever you encounter an object, the tip height has to go up in order to keep the force between the tip and the substrate fixed. And by measuring that motion in Z, that gives you the topography, right? You can then map out the topography of your sample. So that's how it's done experimentally, right? And that's why why it's called a scanning microscope, because you're actually scanning the tip across the substrate while maintaining a constant force between the tip and the substrate. To maintain a constant force between the tip and the substrate, right, that implies that you have some fixed Z on this curve. So you can pick any point, you can pick any value of Z on this curve. Once you pick a value of Z, there's a force. And if you can hold that force constant as you scan, you've got a microscope, right? Because that'll actually map out the Z dimensions of your sample. How do you make springs with sharp tips on them? Well, that was a big problem. Right? Eventually it was solved by making these small microcantilevers, right? So these microcantilevers are a few hundred microns in dimension, in length. Each microcantilever has a sharp tip on the end of it, right? And this microcantilever acts like that spring that I had attached to the tip in the earlier slide. Right? The bending of this microcantilever, I'll show you in a minute, that's exactly equivalent to a spring that is attached to the tip. So in the early days, of course, nobody knew how to make these things, right? And we used to make tips by trying to glue little pieces of diamond onto tiny little wires. It was terrible. They never would work, right? It would only work for a few hours a week. But the semiconductor industry in California has all this technology to etch and make MEMS structures, you know, these very tiny structures in silicon. And so they very eagerly jumped onto this problem. And now you can buy these tips. And cantilevers, they're like $20, $25 a piece, right? And you typically go through 1 or 2 cantilevers a day if you're scanning a substrate, right? So once you have the instrument, the main cost tends to be buying new tips buying sharp tips. Okay, and I have some examples here where you can see how sharp these tips can be made. Right, sometimes they add on very sharp little needles to the end of the tip because the game is to get the tip radius as small as possible. Right, so that when you scan, you get the highest resolution possible. That's the game that's being played. If you study the mechanics of a cantilever, right, what you can convince yourself of is that if the cantilever has a length L and you apply a force at the end of the cantilever, two things happen, right? So if you apply an upward force, one thing that happens is the cantilever bends up, there's a deflection, and there's also a change in the angle of the cantilever. Right, so initially the cantilever is flat. After you push it up, the cantilever has a bend to it, so there's a slight angle theta. There's also a displacement delta. And by analyzing this problem, what you can show is that both delta and theta are proportional to the force F applied. And the proportionality between the force and the deflection, or between the force and the angle, is just a bunch of numbers that depend on the geometry of the cantilever and the material from which the cantilever is made. So E is the elastic modulus of the material. Usually the material of choice is silicon, right? L is the length of the cantilever. I is the areal moment of inertia of the cantilever. So this is geometry, this is materials, this is geometry. So you can calculate that proportionality. There's a proportionality between force and theta, between force and distance, right? And that's all you need, right? Because if I can measure either delta or theta, and I know this, then I can work backwards and get the force, right? That's all I need. So it turns out, for reasons that I won't go into, that most AFMs work by measuring the deflection of the cantilever as it's scanned over the substrate. And if I measure the deflection, then I can get the force by multiplying with those constants, right? There are many ways that have been devised to measure deflections of cantilevers, right? There's almost as many ways to measure deflections of cantilevers as there are people in this room, okay? And I just go through and I list a variety of the techniques. It turns out this idea here was the one that is dominating most AFMs that are built today. So this idea is very simple. It just takes a laser beam. It focuses the laser beam so that it reflects off the cantilever. The reflected light from the cantilever falls onto a position-sensitive detector. And the position-sensitive detector then gives you a voltage, which is proportional to the deflection of the cantilever. So you can calibrate this system very nicely. And so you can calibrate for, let's say, a nanometer deflection of the cantilever. You can calibrate how many volts are going to come out of this position-sensitive detector. So once you know that calibration factor, then you're in. So if you measure, let's say, a volt of output here, that volt of output could translate into 50 nanometers deflection of the cantilever, which is the sort of thing you need to know. If you know the deflection of the cantilever, and if you know the spring constant of the cantilever, then you can calculate the forces that are acting between the tip and the substrate. So it all hangs together very nicely, right? And it's very inexpensive. Very, you know, the laser, these lasers here are on the order of $50. The position-sensitive detector's on the order of $10. So for something under $100, you could measure deflections of cantilevers less than a nanometer, right? Which is remarkable if you think about it, because a nanometer deflection is really tiny. Okay? So that's actually how the instrument works, right? I don't know if any of you studied feedback circuits yet in your courses. We got any electrical engineers here? Oh, so have you had feedback circuits? Some of you? Feedback circuits are amazing because they're designed to keep some quantity fixed, right? And the quantity that this feedback circuit keeps fixed is the voltage out of this photodiode. And the voltage out of this photodiode is proportional to the deflection of this cantilever. And the deflection of this cantilever is proportional to the force between the tip and the substrate. So if I can keep the voltage in the photodiode constant, that means I'm keeping a constant force between the tip and the substrate. If I keep a constant force between the tip and the substrate, think back to that force curve, that means that the separation between the tip and the substrate is also fixed, right? So this feedback circuit, when properly designed, keeps this substrate tip distance fixed as the substrate is moved underneath the tip, as the substrate is rastered beneath the tip. So you image the substrate by moving the substrate beneath the tip, and you keep the voltage on the photodiode constant with this feedback circuit, which is constantly changing. It's constantly adjusting the substrate up and down. So if you get to a feature on the substrate where the tip substrate force goes way up, that means you gotta pull the substrate back again, right? So this feedback circuit gives a signal that says pull the substrate back, the force is too high. And in that process, you actually map out the topography of the surface, right? If you've been listening carefully, you probably realize that the force that we're measuring is due to separations between the tip and the substrate that are on the order of a nanometer or less. The typical vibrations on the floor of this building are tens of microns. So if you build a microscope like this and you just set it on the floor, the vibrations of people walking around, the elevator going up and down, the trucks going back and forth in the street, is going to cause this floor to vibrate by hundreds, if not thousands of nanometers. So how in the world is it possible to hold a tip above a substrate to a precision of a nanometer when the vibrations of the floor which this instrument is setting on is vibrating by hundreds of nanometers? How do you achieve that? Right? How do you mitigate that floor vibration? Big problem, right? Huge problem. The way you do it is you build vibration isolators, right? And the principle of a vibration isolator is that if your floor is vibrating by a quantity delta Z naught, you want to build a isolation system that reduces this floor vibration by a quantity alpha. So alpha is hopefully a number less than 1, right? And so if this floor is vibrating, let's say 100 nanometers, you want to make this platform vibrate by 1 nanometer. That means alpha has to be a number on the order of 0.01, right? Factor of 100 reduction. Well, if you could build one stack like this, one vibration isolation stack, then you can build many. And this is often what was done in the early days. You would build different levels of vibration isolation. Each level would give you a factor of alpha vibration isolation. So if you had n stacks, you would just have alpha raised to the n power times the initial vibration. That's how much your platform would vibrate. And then this mass m here represents the AFM instrument, right? So you would have to build these vibration isolation stacks to eliminate floor vibrations. Otherwise, these microscopes will just be jittering all over the place, right? You won't get anything out. That was in 1986. Nowadays, what we do is we build buildings like Burke, right? So inside of Burke, my lab at the end of the hallway on the first floor, It actually has a 30,000 kilogram slab of cement. This cement is isolated from the building vibrations by 6 inner tubes from automobiles, which are buried. You can't see those. You have to actually go underneath the floor. Here's a guy coming out. So if you pull up one of these panels, you can go underneath and you'll see these big inner tubes, right? That slab vibrates less than a nanometer at frequencies above 10 hertz, right? So it achieves factors of 1,000 vibration isolation over the vibrations that are running around on the floor of the building out here, right? So what we do now is, knowing the importance of these scanning probe microscopes, right? The current trend is to design buildings and rooms inside of buildings which are vibrationally isolated. And then you put your microscope on this slab. You put all the electronics on the floor surrounding it. The slab is separated from the floor. And it's beautiful, right? So when I moved from physics to Burke, I went from a situation where in physics I could, not me, my students could only take data like after 6 p.m., right? So we did a lot of night work, because by then all the trucks on Northwestern and all the students running through the physics building taking physics classes, they would all leave and things would settle down. And so we would come in and take data from 6 until 1 or 2 in the morning. You move to Burke and you put your instrument on this slab and you've got 24/7 operation. You can come in any time of the day, any day of the week, and you're guaranteed that the vibration isolation is going to be good. So this is a big breakthrough for us that we're doing scanning probe research. So, but it requires a building like Burke, right? You can't retrofit this type of vibration isolation slab into an existing building. You can do it, but it's extremely expensive. It's better to design it with the building, and that's what, fortunately, we did here. Okay, we also have to achieve nanoscale motion, which is vibrationless. So when we move this tip, right, I was talking to you about moving the tip over the substrate in a systematic and controlled way. How are you going to do that? You just can't hook up a motor. You can't turn a gear or a micrometer, right? Because anytime you do that, you're going to introduce all kinds of uncontrolled vibrations. So what you need to do is you need to be able to build a system that you don't have to touch, but you can control positions. And of course, the way to do that is piezoelectricity. I don't know if you've studied about this yet in your courses, but it's an amazing effect, right? It was discovered in the late 1800s. Piezoelectricity says that if you put a voltage across a piezoactive material, so this is my piezoactive material, right? And I put a voltage across it, right? The length of the material in this direction will change proportionally to the voltage that I apply. And I don't have to touch it. I don't have to do any mechanical motion. I just apply a voltage with a battery, right? How much does it exchange? How much does delta L, how much does L change? Well, delta L is proportional to the length L, and it's also inversely proportional to the distance H, the thickness of the piezo block, right? And then there's a constant, a piezo constant, that depends on the material that the block is made from. So these numbers D31 are known. L, you can cut these piezo blocks to whatever dimension you need. You can fashion them to have different heights, different thicknesses. And so in this way, by just applying a voltage, right, you can cause the tip to move in a controlled way back and forth without any vibration, right? And this is a key feature in all scanning probe microscopes. This is what they did in the early days, 1981, 82, and it's still used today, right? So this piezoelectricity is a really cool thing. The entire system looks something like this. So if you actually want to use one of these microscopes, right, you're going to be sitting out here at a computer control, right? And this computer control is going to issue commands to various modules. These various modules are going to control the feedback of the tip with the separation of the tip from the substrate. They're going to, if you put voltages on your tip, there's going to be a voltage control. You're also going to have an XY scan control. So these are the scanning signals that are going to move the sample in X and Y while you record Z. So you have to use this instrument, you have to be able to interface with the software that's been written, right? And the advantage of doing it is you get these beautiful three-dimensional images of samples at length scales that are tens to hundreds of nanometers in extent, right? So the hard part is learning the computer control software. Every system, every AFM that you sit down and use is going to have a different set of assumptions and approximations and subroutines, and you have to master all that and make it work as a whole. Right, so the systems are getting much better now than they were 20, 30 years ago, right? Everything's becoming much more integrated, makes it easier for you as a student to use these instruments. But it still requires a few months of practice. I will say, I just put this up, we had a bet in my lab that once all the electronics is built, all the computer software is written, one of my students felt that he could actually build a scanning probe microscope that would see atoms in one day, right? And so we had this bet, and this is the instrument that he built. He put it together in under 8 hours, right? What it is a very fine micrometer. This is a flexible board. Here's the tip. Here's the substrate. Here's the piezo that controls the motion of the substrate. You can see everything's made out of brass, and it's just cooked up in the machine shop. And when he put all this together and hooked it up to our electronics, he was able to see the periodicity of atoms in this substrate. So these bright spots, right, if you look at this picture, you'll see that there are a sequence of bright spots that are periodically positioned in the image. Those individual bright spots are the atoms that comprise the substrate that's attached to this piezo tube. So within a day, he was able to put together a system that allowed you to see atoms, right? Assuming you already had all the control electronics put together. So these things tend to be simple. This is not a research grade instrument. I don't want to pretend that it is, but I'm just trying to convince you that if you know what you're doing, you understand these principles, you can put together an instrument on your own to see atoms in one day, okay? So I think that's an incredible achievement. So I'll just end by showing some typical images, all right? I just went to the web and pulled off some different images. I have an example from electrical engineering. So this is a little island of material, and these are gates, source, drain, and gates, and they're trying to pass electrons through this island. And what they wanted to do is they wanted to image the topography of their device with an AFM. So these are the different electrodes, gate electrodes, guard electrodes, the source and the drain, right? So this is an application from electrical engineering. This is an application from biology. So these are red blood cells, 3 red blood cells, right, that were imaged. So a blood cell is about, 3 or 4 microns in diameter, right? So that gives you the scale of this image. This is an application from magnetism, and this is a sample, and these stripes, these bright stripes, show different regions of the sample magnetized with different orientations, right? So they were able to image the magnetization of this sample using an atomic force microscope. And then this example, this is a friend of mine from Spain. He imaged this is a DNA molecule, right? So he put a strand of DNA on a substrate, and he imaged it, and he actually took the tip and he cut the DNA right here. So you can see it goes back. It just shows you that you can manipulate. You can actually start to tailor strands of carbon nanotubes or DNA molecules by using the tip to actually perform some nanomanipulation. So just a few examples. This, in my opinion, is one of the best studies that have ever been done. This was done by another friend of mine, Oscar Costanza. He was working in Japan, and his group, the group that he worked with over there, was actually able to image atoms on a surface. And by measuring the difference in the force between the tip when it was positioned over each atom, they were able to identify the atoms in the substrate. Right? So the force between the tip and each different type of atom is slightly different one from another. It depends on what the atom is made from. So in this sample, they had silicon, tin, and lead atoms, and they went and they positioned the tip over each of these atoms. They measured the force versus distance, and by measuring that force versus distance, they were able to color all the silicon atoms red, all the lead atoms green, and all the tin atoms blue, right? So they were actually able to identify atom by atom the chemical composition of their substrate. So this to me is just like unbelievable, right? This is really good work because it's really getting down to the nanoscale, and it allows you to start to color atoms, right? So, right, if you ever wanted to know the difference between a silicon and a tin atom, well, one's red and the other's blue, right? So, very nice piece of work, okay? Has not been, in my opinion, there's nothing better than this. So, I've been looking at this topic called nanotechnology for 28 years, and I looked through it through rose-colored glasses, right? Because the glasses I use are based on this scanning probe microscopy. Right, so my entire research has been based on looking at nanotechnology through the eyes of scanning tunneling microscopy and atomic force microscopy. And it's been just an incredible adventure watching how this whole field has developed over those years. If you're truly interested in this topic or in this subject, or if you have friends that might be interested in learning more about it, I'll tell you that at Purdue we have complete set of NanoHub courses devoted to scanning probe microscopy. They are pitched at a higher level than freshmen and sophomore undergraduates, right? You need to know a little bit of upper level physics and mechanics to appreciate these online courses, but they're there available to you or to any of your friends to look at. And then coming soon, we're trying to get a book out with World Scientific that will cover a lot of the fundamentals of atomic force microscopy that I've tried to outline here today. So if you're really interested, you can possibly look for the book. It should be out by first of the year. So I'll stop because my time is up, and I'll be happy to answer any questions you might have, and I'm hoping that there are a lot of questions. So thank you. Yeah.
I was going to ask, do you change what the material of the tip is depending on what substrate you're analyzing?
Yeah. Yeah, there are different types of tips, and you can coat those tips with different types of materials. So you can gold coat the tip, you can put platinum on the tip, you can functionalize the tip with chemistry. So you can put molecules on the tip, right? It's a cottage industry, right? Now the trouble is physicists aren't very good at chemistry. So what we tend to do is we tend to establish collaborations with chemists who know how to coat the tips with molecules, right? Physicists aren't very good at depositing thin films. So we tend to collaborate with people from, let's say, the clean room who might know how to deposit thin films, right? And so that's one aspect of this microscope that I didn't mention. but it's an extremely collaborative endeavor because it seems like no one person has everything under control to do a really cool experiment. So you need somebody that has a special sample, somebody that could make a special tip, somebody that could make the instrument work, right? And so it tends to breed an intercollaboration in the research, which to me is a definition of nanotechnology, right? I assume you're all here because of nanotechnology, is that true? Yeah. So that's a really cool aspect. It's a social aspect of AFMs and STMs that I don't think anybody could foresee back when they were invented, right? It's extremely interactive, very, very interesting. You're always learning new things, you know? So that's nothing wrong with that. So yeah, many tips. Yeah. Yes.
The sort microscopes are much cheaper than, say, the electron microscopes, and they have these capabilities, then why are there still electron microscopes? What's their...
Oh, you never throw away a good tool, right?
Like, so, I mean, is there an advantage they have over...
The scanning electron microscopes tend to be much easier to use. So if you're just trying to get a very quick image of, let's say, a silicon wafer that's got trenches in it, you just want to measure the width of the trench, usually it's much easier to do that with an SEM than it is with an AFM. The scanning electron microscope, of course, has been around a lot longer. So there's a huge group of people that know and trust and believe it. And so they're very reluctant to switch horses in the middle of a game. You know, they don't want to make a change. They're comfortable with this technique, so they want to use it. Those of us that grew up with scanning probe microscopes were more comfortable with the scanning probe microscope compared to the scanning electron microscope. So we tend to use it, you know, so there's a lot of reasons. But I would say they still provide complementary information, right? Each has their own strong point, right? But I'm told that on fab lines in semiconductor industry, they need to have like 3 SEMs, and they're constantly checking the calibration of one with respect to the other, because, you know, they need to know the separation between 2 lines very accurately to make their chips work. And if they put it into one SEM, they get one answer. They put it into another, they get another answer, right? Because the calibrations are very critical, right? They depend on voltages and things I don't understand. So, you know, if you're doing really careful work, you constantly got to be checking calibrations with the SEMs. And that means you have to have more than one SEM to do that. You know, if you're doing university work, it's probably not such a big deal, because, well, everything's got its pluses and minuses, right? Yeah.
Are there any other kinds of microscopy that people are trying to develop now?
Well, there are advanced types of optical microscopy, right? There are advanced types of electron microscopies, right? So some electron microscopes, for instance, use the spin of electrons to get information about the magnetic properties of a sample. So I would call that a specialty application of an electron microscope. Optical microscopes, they've got Raman imaging now, right? Where you can map out a Raman signal as a function of position. That wasn't possible 5 years ago, right? So that's based on optics, but it's a sort of an advanced application. And in the scanning probe world, we also have these specific advanced, what I would call advanced applications, that are tailored by experts to address one particular question. So I think that's common across all the areas, all the branches. So, yeah.
You say that you use the voltage to move the tip. isn't there a possibility that that voltage could interfere with the force between the tip and the substrate?
Yeah, there's a question about we use the voltage to move the tip, and could it be that that voltage could interfere with the forces? And that's certainly true. If you put that voltage right on the tip, right, and if your sample was grounded, then there would be a capacitance between your tip. Well, there's always a capacitance between the tip and ground. You put a voltage, right, then there's going to be a force, and the tip is going to bend due to the voltage that you apply. So what you have to do is you have to be very careful that the voltage you apply to move the tip doesn't leak onto the tip itself, right? So you just have to build insulating layers and electrically isolate things very well, right? But when you build these instruments like we did back in the 80s, right, those were all kinds of issues because it's like, oh, geez, there's a short. Where's it at? I don't know. And, and then you'd have to figure it out. So, but a lot of that's taken care of now by the companies because they make these things now and all those details are sorted out. Yeah.
Is the resolving power of these scanning probe microscopes basically set at one atom because you're detecting at the tip with just one atom at the tip, so you can't go much smaller than that?
That's correct. The best you can do is 1 atom resolution. Okay? There have been some claims that you could use the AFM to resolve the chemical bonds between atoms in the substrate. Those chemical bonds are very directional, right? And there have been some claims that those have been imaged, but I don't think that's widely accepted. Okay. And of course, you have to work to get a sharp tip because if your tip has got 10 atoms on the apex, it's much harder to see 1 atom in the substrate when your tip has got a radius that's large. So thankfully, most people don't want to see individual atoms, right? Most engineers, all they want to do is measure the depth of a trench or the width of a trench or the height of a plateau, and that's in hundreds of nanometers. That's not a problem, right? But the really scientific work where you're trying to push atomic resolution, there's maybe only a dozen or so labs in the world that are good enough to play in that sandbox. It's pretty challenging work, right? So I don't want to give you the impression that every AFM sees atoms, right? If you want to see atoms with an AFM, you got to work at it. You have to have a research program that's focused on that goal. But routine characterization of samples, that's here, right? Any commercial instrument you buy nowadays or any instrument that you might find in your research labs would be able to do routine characterization. Okay? Great. Well, thanks for coming. I really appreciate your attention. Thanks for not using your cell phones during the talk. And I hope you have a chance to use one of these instruments before you get out of college because it's a real eye-opener. So, thank you.